3, 2, 1. Reduction time. All right. Okay, so we have set the stage for what we need to do. We want to solve second-order linear differential equations. The first step is to solve the homogeneous case, so when the right-hand side is equal to 0. And as we noted, the solution to such equations will always be a linear combination of two linearly independent functions, right? And we call these a fundamental set of solutions. Okay. Right, so in order to solve second-order linear homogeneous differential equations, just find two solutions, verify they're linearly independent, scale them up, add them together, and we're done. Okay. So, as we've seen so far, the way we've been solving these has been just by inspection, right? We've been looking at maybe some canned examples of DEs, where sort of it's pretty easy to detect what the solutions need to be. And this is actually pretty much the typical situation for second-order linear differential equations. You can find one of the solutions pretty easily, right? There's something about the equation, there's something you can quickly notice and just go, oh, this works. This function obviously is a solution. But the other one is not so immediately apparent, right? So for nice example, give this one a go. X squared times y double prime minus x times y prime plus y equals 0. So again, let's read it. Let's think about what it is. I want to find a function so that its second derivative times x squared minus its first derivative times x plus itself has to equal 0. Aha! So, you may not have noticed it, but your brain certainly did. X pretty easily works, right? X's first derivative is 1, and its second derivative is 0. So when we plug it into the DE, well, the y double prime term is just gone. Y prime is 1, so we have negative x, and y is x, so they add up to 0. Nice. Okay. So, right, this may be, you might be a little like, oh, come on now. Come on now. How was I supposed to see it? Well, now that you see the answer, it's pretty obvious that should have been something to try, right? Because if we plug in a polynomial, right, again, read it. I've got polynomials and derivatives being added up, and the derivatives lined up with the order of the polynomials, right? One derivative, first power, second derivative, two powers, no power, no derivative. The other way around. No power, no derivative, right? Oh, okay. That might be something. So it's pretty easy to see that x is just an answer to this, right? It's easy to verify that, yeah, x is clearly an answer. Okay, so we have one of the solutions. So all I have to do now is find the other one and verify that it's linearly independent. All right, well, what is it going to be? Well, I'm telling you right now, unless you've already taken this class before, you've got no idea. You're never going to guess what the answer is. Right? You will never stumble upon the solution accidentally. Even if you were to pause right now and go like, I'll show you, you'll see. If you do guess it, it's a real slick guess. It's not immediately obvious what the other solution should be. But this represents a situation that you find yourself a lot in when you're dealing with second order DEs, right? You could cook up the first solution, no problem. But now you're faced with, all right, well, how do I find the other one? Okay. Well, remember, the whole conceit here is that I need a fundamental set of solutions. I don't just need solutions. I need really good solutions. I need linearly independent solutions. So a fundamental set of solutions are a pair of solutions that are linearly independent. And being linearly independent means that when I look at the ratio of the two functions, when I look at y2 divided by y1, this cannot be a constant. If this was a constant, then that would mean that y2 is equal to some multiple of y1, where c is a scalar. That contradicts the linear independence. Oh, okay. So that means that y sub 2 divided by y sub 1 is got to be a function. It can't be a constant. In other words, here's the key ingredient. We only ever actually need to find one solution to our second order linear differential equation. We know that their solutions have to be linearly independent. That guarantees that their ratio has to be some function, and that means that y2 has to just be y1 times something. So I just need to figure out what that something is. Okay, so let's go back to this differential equation, x squared y double prime minus x times y prime plus y equals 0. We know that one of the solutions is just x. Well, since we know that the solution needs to be, the general solution to this DE needs to be a linear combination of linearly independent functions, we know that y sub 2 needs to be some function times x. So we just got to figure out what that function is. Now, how can we do that? Well, y sub 2 satisfies the differential equation, so let's plug it in. All right. So we know that 0 has to be x squared, y double prime, y sub 2 double prime, minus x times y sub 2 prime, plus y sub 2. We know y sub 2 is u times x, so plug that in. And let's do a little housekeeping. So I did the first derivative, I did the second derivative. Note the second derivative. Just take this derivative of this thing again. You'll get that. Product rule is occurring here, remember, because u is a function. So I have u times x. So product rule applies when I take the derivative. So it cleans up nicely. And now this last step I did, this might at first glance be a little weird, but this is something that you're going to want to do. Right, I want to get u double prime by itself. So I factored out the x cubed. That is, from experience, doing that. When you first look at this, you might only think to factor out x squared. It's actually going to be better to factor out x cubed. Get the u double prime by itself. So what do we have now? We've got x cubed times this. Well, x cubed is not identically equal to 0. So the only way this could have possibly held is if this term was equal to 0. Right. And note, I've made a move here where I've implicitly assumed that I'm not going to allow x equals 0, and that's because, well, right, look, x is multiplying the derivative, so we can't let x equal 0, otherwise, right, we get that, the weirdness we saw when it came to linear first-order DEs, so, right, again, if we were going to be really precise, we'd be paying a lot of attention to the domain of the independent variable, but we're going to play fast and loose in this class. But, all right, well, I did this, and I got that, so why do I... Okay, yeah, sure, this is something I can do. Why do I care? Why am I happy now? Again, you may not notice it, but your brain does. We are in a great position, right? In fact, we're in the end game. Let's make a little slick substitution. Let's let v equal the derivative of u. That means the derivative of v is the second derivative of u. So my differential equation, u double prime plus 1 over x u prime equaling 0, is actually v prime plus 1 over x times v equaling 0. So the order of the original differential equation now has been reduced. I had a second order DE I was working with. I've now reduced it to a first order DE, and high five, it's separable. It's actually linear too, but let's treat it as separable. So this is a slick move that we just pulled off. Okay, so we can now solve this first order separable DE. There's the details of it. Subtract the 1 over x over. Remember, v prime is dv dx. Cross multiply the dx, divide over the v. Again, I'm not getting too sweaty about log of the absolute value. Remember, negative log is equal to log of 1 over x. Very important fact. And hey, log of v is log of 1 over x, so that means that v has to be 1 over x. Okay, so we did a bunch of work now. Let's remind ourselves what we're doing and why we're doing it. And, right, it's always good to pause and go, all right, I just did a bunch of stuff. Why'd I do it again? Okay, so we have now that v is 1 over x, and we know what v was. V was u prime. U prime is 1 over x, so that means that u needs to be log. Note, I'm not caring about constants, because, what are we trying to do? We're trying to solve a second-order linear differential equation. I just need two solutions. I will scale and add them up later, so I don't need to include any scalars as I'm going forth here. I don't need to do the plus c nonsense that we normally do when we're doing when we're solving integrals, as we did in calculus. Okay. So what did we know? Well, we had one solution, y1, which was x, and because of the linear independence of y1 and y2, we knew that y2 had to be u times x. Well, we just figured out what u is. It's log. And boom, there we go. y2 is x times log x. And as I promised, there was no way in hell you were going to guess that. So we can now conclude, because remember, the way this works, this y sub 2 we created has to be linearly independent from y1. It was built into the method that it was linearly independent. So I actually didn't need to check that. I'm implicitly using that fact to create this general solution. So I had my first solution, x, that I found by inspection, and then I went through this process to create the second solution, and big old typo right there. It's not just log of x, it's x log x. Let me go ahead and fix that. Boom. Prestidigitation, there's the x log x. Man, not too bad. One typo a slide is pretty good, gotta say. That's like the problem when you type up mathematics. In your head, it makes complete sense and it's totally right, but then somebody else looks at it and goes like, dude, what's going on? This isn't right. Get in my head, come back out, tell me I'm wrong. But anyway, so there we go. All right, so now we've seen something quite interesting. So as we've motivated, if we want to solve a second linear order differential equation, we need to first solve the homogeneous, then find a particular solution. Solving the homogeneous, as we discussed, boiled down to doing two things: finding two solutions and verifying they're linearly independent. Now we just demonstrated that actually, if you find one solution, I can now go through this method to create the other one. And built into the method is ensuring that the function I do get is linearly independent from y1 to begin with. So we've actually now made it even easier. If you want to solve any homogeneous second-order linear differential equation, just find one solution. You can then create the second one using this technique. Okay, so obviously, this technique has a name, and as you are no doubt guessing, there's probably a better way to do it. So, y sub 1, if that's a solution to a second-order linear DE, note the form it is in. I want to stress this. Note the form that it is in. Then the second solution can be found, exactly as we just discussed, by multiplying y1 by u, where u is this expression. All right, there you go. So, as we had already seen, the way this works is that it's going to reduce the order. So I'm not going to work out the details of how this is why u is always equal to that. I'm just stressing, of course, that, hey, note the form I put it in. This is known as the standard form of a second-order linear DE. So that whole process that I just went through, there is a quicker way of doing it, where the u is always going to have a nice form. Nice, with some big quotes around that. So if you want to see the derivation of this formula, it's in your textbook, go ahead. I used to derive this for people. It's worth going through for your own mathematical health, but it's a little involved. You can go look it up. There's a couple of cool spots, but it is one of those things where it's a lot of work, so I'm not gonna get into it. But anyway, now that we have it, let's give it a spin, right? Because now equipped with this, solving a second-order linear homogeneous differential equation boils down now to finding one solution and then using reduction of order to create the other. So it's even less work than I originally told you, right? So if you want to solve it, you don't even need to find two solutions now. You just got to find one. You got one. Here's how you create the other one. So it's even easier. All right. So let's give it a go. Here's a DE for you. a DE that I'm very fond of. This is one of my favorite differential equations. This might be my favorite differential equation of all time. So, if you want to solve this, all you need to do is find one solution. Just find a solution. Anything that makes this work. Once you've got it, you can reduce the order to get the other one. Okay. So, this is a great time to pause the video. Give it a go. Can you find the solution? I claim it's really obvious. Right? Can you figure it out? I claim, I'll make it even easier for you. The solution is one of the coefficients. Alright. Okay, you get it? So, cosine is an answer, right? If you plug in cosine, secant times cosine is 1, right? Secant is 1 over cosine. The derivative of cosine is minus sine. The second derivative of cosine is minus cosine. So we've got a plus 1 here, a sine squared, cosine squared. Remember, that adds up to 1. And hey, minus signs. Beautiful. So, this differential equation has a pretty easy solution to find. Cosine of x. Right, just by inspection, you can find it. So, fun story about this. I put this on an exam once. And I said, solve this following differential equation. I did give the hint that one of the solutions is one of the coefficient functions, so you can actually just check 3 things, and the first one works. So I love this. And what I love about that problem, I put that on an exam, and I put that on there, and I was like, this is going to be the one that's going to suck the grade. Right? You always got to put one problem on an exam. So this is like as like a teacher, I guess. I'm like, you always get the one problem. It's like this is going to be a nightmare to grade, right? Because it's good for everybody's health to attack a tough problem like this. And I was really surprised because everybody got it, and I was like, that hint was too easy. Right? If I didn't give that hint, nobody would do anything. But right, because once you get the cosines an answer, it's really easy to use reduction order to create the other one. So let's do that. So remember, in order to use that formula, I actually have to get it into its standard form, the appropriate form. So first I got to clean it up. So I got to divide it out by the leading coefficient, and then note that that's a typo right there. That should be 1 over cosine, secant over cosine. See, I was all excited about the secant squared. That's what was going on there. All right, yeah, so sine over cosine, of course, is tangent. 1 over cosine is secant, so I got secant squared there. So here it is in its appropriate form. The reduction of order technique now tells me that u is the integral of e to the negative integral of the coefficient of y prime, which in this case is tangent, divided by the solution that we found, which is cosine, quantity squared. Right? And if you're cringing at that going, that sounds like a complete nightmare, don't worry, it's not. The integral of tangent, if you don't have this one ready to go in your head, it's negative log of cosine. That one's easy to solve. Remember, tangent is sine over cosine. Then let u equal cosine. It's a pretty straightforward u substitution. All right, e to the log, of course, jailbreaks the cosine. Cosine over cosine squared gives me 1 over cosine, which is secant. So now we have to integrate secant. All right. So, fun little sidebar for today. The integral of secant. Now, you learn what this is in calculus. Spoilers, it's log of secant plus tangent. So, the integral of secant, right, here's a fun fact for you. The integral of secant was probably the first famous problem of calculus. Right. So, right, once calculus started going in, especially once the idea of a derivative was put together, then the idea of any derivatives going backwards comes into play. And secant actually makes a lot of appearances in navigation. And so figuring out its antiderivative was very important. And at first, right, this became like the challenge, to figure out what the antiderivative of secant is. And, right, it was kind of like the first big unsolved problem in calculus. Ooh, what does this get equal? And so as you learn, the way you derive it is to use partial fractions. So it's 1 over cosine, and then what you do is multiply top and bottom by cosine, so you get cosine at the top and 1 minus sine in the bottom. Sorry. So it's 1 over cosine, and so it's actually better to attack it as cosine over cosine squared. Then replace this by 1 minus sine squared, do a u sub, and then now you're dealing with 1 over 1 minus u squared, and then you can partial fractions that. So it's actually the first time partial fractions was used to solve the DE. So to solve an integral. So the fun little calculus history there. I forget the name of the guy who figured it out. It wasn't Newton. It was somebody else. Oh, beats me. But anyway, so it was like the first big problem in calculus. Figure out the integral of secant, which is log of secant plus tangent. So again, the first solution, cosine of x, easy to detect. But the second solution, right? No way were you going to guess that, right? When you look at that, it's like no way you could have guessed that. Okay, so here we see, even if one solution is a little obvious, the second one is not necessarily so much. But, alright, now equipped with that, we have the general solution to the DE. You've got y1, you've got y2. That's it, and we're done. Okay, so we've now learned that if I want to solve homogeneous differential equations, you just need to find one solution. Then you can reduce the order and walk away. Beautiful. Cool. Alright, well, I think it's probably time we should talk about how you actually would even find that first solution in the first place, right? Yeah, just guessing answers or inspecting things. I mean, that works, but it'd be great if we had a formula, or that'd be nice, right? Maybe there is one. Let's talk about it next time.